Did you know that logic formulation is like giving super clear instructions to a computer? Similar to teaching a robot how to cook noodles step by step? If you forget even one step, the robot won't know what to do. That's why logic formulation is so important in programming. Good day, everyone. I am Ravi Garcia from BSCS 1B, and today I'll be presenting about logic formulation for our subject, Fundamentals of Programming. Before we dive in, let me share with you the objectives of this lesson. First is to discuss program logic formulation. Second is to identify and explain each step involved in the programming cycle. Third is to explain the use of an algorithm. Fourth is to determine the procedure of pseudocode. Fifth is to recognize the use of each flowchart symbol. And lastly is to illustrate and design flowchart. Flowchart. So these objectives will guide us throughout the presentation. So first one, what is a computer program? A computer program, also known as software, is simply a sequence of instructions written to perform a specific task for a computer. Think of it like a recipe. The instructions are written step by step, and the computer follows them exactly. For examples include programming, languages like Java, C++, and Visual Basic. Now let's jump into the programming cycle. This is the process programmers follow to build a program. This has 4 steps. Number 1 is the problem definition. First, we clearly identify the problem. For example, if the goal is to compute student grades automatically, the definition should clearly say the program must calculate the average score and display if the student pass or fail. The next one is the problem analysis. We break down the problem into parts. We ask questions like, what are the inputs? What process should be done? And what should the output be? In our grade example, inputs are the student's quiz and exam scores. The process is computing the average. The output is the final grade with a remark, pass or fail. Next is the algorithm development. The algorithm development, once we understand the problem, we create a step-by-step solution. For example, step 1 is to get the quiz and exam scores and add them together, divide by the total possible score, and if the result is greater than or equal to 60, display pass, otherwise display fail. This algorithm is our blueprint before we start coding. And lastly, we have coding and debugging. Finally, we translate the algorithm into code using a programming language like Java or C++. At this stage, errors or bugs can appear. Debugging means testing and fixing these errors until the program works correctly. Now, let's jump into the algorithm. An algorithm is basically a step-by-step problem-solving procedure. It must follow three characteristics. Number 1 is each step must be specified clearly, or in other words, specify tasks or instructions exactly. Number 2 is there should be a finite number of steps. And lastly is there must be always an output. So in short, An algorithm is like giving very specific instructions that always lead to a solution. Next is we have the pseudocode. Since algorithms are still very general, programmers often write them as pseudocode. Pseudocode is a way of writing instructions that looks like code, but it doesn't follow the strict rules of any programming language. It cannot be executed on a computer, but it helps us plan our program because it's close to real code and easy to understand, unlike the actual programming code. Example of the pseudocode is if a student's grade is greater than or equal to 60, we want to display passed, otherwise display failed. So in pseudocode, we would simply write if grade is greater than 60, print pass. Else, and we put the right arrow, print failed. So this is a simple and clear, and it prepares us for real coding later. Now is the steps in problem solving. Is to summarize problem solving. First, we create a general algorithm, often written in pseudocode. Then we refine it step by step until it's very close to a computer language. So pseudocode is helpful because it's written in everyday English, making it easy for programmers to develop solutions. Now let's go on to the flowchart. So a flowchart is a visual representation of an algorithm or a process. It uses symbols and arrows to show the steps and the direction of flow in a program. Each symbol has a specific meaning, and when combined, they help us visualize the logic of a program even before writing any code. There are several types of symbols used in a flowchart. The terminal block, which is an oval shape, indicates the start or end of a program. The process block, a rectangle, represents an operation or a calculation, something the computer needs to perform. The input or output block, drawn as a parallelogram, handles data entry or display, such as getting a value from the user or showing the result. The decision block, which is a diamond shape. This block represents a condition or decision point in the program. It asks a question, and based on whether the answer is true or false, the program follows one of two paths. There are also connectors and flow lines that help link different parts of the flowchart and show the direction of movement between steps. Flow lines are the arrows that connect the symbols. They show how data or control moves through the program. It's important that flow lines are neat and clear. Avoid crossing lines or making the flow confusing. Next is the terminal block. As mentioned earlier, is used at the start and end of a flowchart. We label the beginning as start and the end as stop or end. The start block only has an outgoing line, while the end block only has an incoming one. Next is the initialization block. This is used to declare and assign initial values to variables. For example, if we set x equals 10 and y equals 25, we're preparing these variables to be used later in the program. The process block is used whenever there's a computation of an operation, such as x equals y plus z or a equals 18. Every process block should have one entry and one exit, so the logic remains easy to follow. The input and output block handles the reading and displaying of data. For example, when we write get x, it means the program accepts input. When we write display x, it means the program shows that value to the user. Next is the decision block. As we discussed, is used when the program needs to make a choice. It checks a condition and can take two different paths, one if the condition is true and another if it is false. For example, if x is greater than 10, the program might display pass, otherwise it displays fail. Connectors are also important in flowcharts. An on-page connector shown as a small circle connects 2 points on the same page while an off-page connector, shaped like a pentagon, connects flowchart parts that are on different pages. These keep our flowchart organized and readable. Let's take a simple example. Suppose we want to create a flowchart that shows our age 5 years from now. We start with a terminal block labeled start. Next, we initialize our age, for example, age equals 18. Then we add a process block that calculates age equals age plus 5. After that, we display the new age using an output block. And finally, we end with a terminal block labeled stop. This flow shows the basic logic from start to end. Now that we understand flowcharts, let's move on to decision structures. Decision structures are statements that result in a Boolean value, either true or false, or in numeric form 1 or 0. These structures allow a program to make decisions depending on conditions. In programming, conditions are divided into two categories: logical operators and relational operators. Conditional statements are what we use when we want our program to behave differently depending on a condition. There are three basic logical operators that can be used in conditional statements: and, or, and not. The and or operators are commonly used to combine multiple conditions, while the not operator is used to reverse the result of a condition. Let's look at how the not operator works. The not operator simply flips a Boolean value. If something is true, not makes it false, and if it's false, not makes it true. In a truth table that looks like this, when condition A is false, not A becomes true. And when condition A is true, not A becomes false. Now, let's move on to the and or operators. These are used when we have two conditions to check. For the and operator, both conditions must be true for the overall result to be true. If either one is false, then the entire expression is false. For example, if we have two conditions, condition A and condition B, and will only be true if both A and B are true. Otherwise, it will return false. For the or operator, we only need one of the conditions to be true for the result to be true. The only time or returns false is when both conditions are false. These logical operators, and, or, and not, helps us create more complex decision-making logic in programs. Now, let's discuss relational operators. Relational operators are used to compare two values. They determine whether one value is greater than, less than, equal to, or not equal to another. After comparing, they return a Boolean result, either true or false, depending on the outcome. Here are the most common relational operators. As you can see here, the less than symbol means one value is smaller than another. The greater than symbol means one value is larger. The less than or equal to symbol means the value is smaller or exactly equal. The greater than or equal to symbol means the value is larger or equally or exactly equal. The double equals means both values are the same. And finally, these two right here means the values are not equal. The one with the exclamation point and the one with the greater than and less than symbol. For example, if we compare x equals 5 and y equals 10, then x is less than y would be true because 5 is less than 10 while x is greater than y would be false. Relational operators are the foundation of making comparisons inside conditions, and when combined with logical operators, they allow us to create powerful and flexible decision-making in our programs. To wrap up everything we've discussed, let's summarize the key points about logic formulation. So logic formulation is the process of planning and organizing the steps needed to solve a problem before we even start coding. It makes sure that our instructions are clear, logical, and easy to follow. First, we have the algorithm, which is the step-by-step procedure for solving a problem. Think of it as the backbone of our solution. Next is pseudocode, which is a simplified way of writing the algorithm using plain English mixed with programming like words. It cannot be executed on a computer, but it helps bridge our ideas into real code. We also use a flowchart, which is a diagram that shows the sequence of steps with symbols and arrows. This visual tool makes it easier to understand how the program flows. Then we have the decision structure. This is used whenever the program needs to choose between two or more paths, like checking if a student passed or failed. And finally, we have conditional statements, such as if and else, which bring these decisions to life in actual programming. They allow the computer to act differently depending on the situation. In short, logical formulation ties all of these together. Algorithms, pseudocodes, flowcharts, decision structures, and conditional statements to help us design programs that are logical, organized, and effective. And that concludes my presentation. And my name is Ravi Garcia from BSCS 1B. I hope you understand something from my discussion, and thank you all for listening. Bye-bye.